Given we have now the basic behavior of a capacitor, its IV relationship, and we have the IV relationship for a resistor, it might occur to you, what if we put them together? And this generates one of the sort of the next most useful circuit we have after the voltage divider. We're going to put them in series. You can put them in parallel, just like we can put resistors in parallel, but this is enough to do some interesting things. So we have an R and a C in series. Now it's possible, using the IV relationships of the resistor, Ohm's law, V equals IR, and the capacitor, I equals C dV dt, to actually derive what we need. The way you do that turns out to be a simple differential equation, and I don't think it's actually that profitable for me to go all the way through it. So instead, I'm going to argue what the shape of this response must be. And then we'll find that these two units give us a key factor we need in understanding that shape. So first, let's think about this. Let's say that I have this source up here. This is now a function generator. And I'm going to make this a step function in time. Let's just plot that right here. So it's going to be 0, and at some point, it's going to step up. What I'm curious about is what I will find over here on the capacitor. And I think we can do a couple points on that graph, the V capacitor, just by intuition. So let's think about that. When we say that the source is 0, we mean it was 0 for all previous time. Capacitors have charge on them, they have history. We always have to sort of formally say, how did we get here? So we'll assume that the capacitor has been sitting with a 0 source voltage across it for some very long time. Maybe this is t equals 0. So at t equals 0 and before, presumably the voltage on the capacitor is 0, because everything's boring. And at some very long time out here, then the capacitor voltage ought to equal, I'll call this V0. V0. Why is that? Well, just think about what must happen. We're basically blowing up a balloon here. We're going to, when we turn the source on, when it switches up, we are going to start charging up the capacitor. There's going to be current that flows through the resistor that builds up charge on the capacitor. As time goes on, more and more charge is going to end up on those capacitor plates until eventually the amount of charge on the plates is going to be such that the capacitor voltage equals the source voltage. There will be 0 voltage across the resistor. That means there's no current, and everything will drift to a halt. This is just like blowing up a balloon or emptying a bucket, where as a function of time, early on, there's this big driving force, this rush of charge onto the plates. But as the charge builds up, it reduces the amount of voltage across R, therefore the amount of current through R, until eventually the capacitor comes up to V source, and there's no current through the resistor at all. So at very long time, we should charge the capacitor up such that the source voltage is dropped across the capacitor. The capacitor is fully charged. And then the question is, what goes on between here? What's that function? If you look at physical systems, water's draining out of buckets, air blowing out of balloons, any simple system where the driving force for, in this case, charging up the capacitor, starts instantaneous, but then that driving force itself is going to decline as the capacitor charges up, you get a shape like that. And the nature of that shape is this. This curve right here is, as a matter of fact, V0, 1 minus, the 1 minus is just the details to get the right way up, e to the minus t over some unknown time constant. I'm going to call it tau, because I like Greek letters. So let's see if that function seems to make sense if at t equals 0, e to the 0 is 1, 1 minus 1 is 0. Oh, yeah, that's that point. And when t goes to infinity, e to the minus infinity is 0. Oh, yeah, so at an infinite time, the function goes up to v0. And we could derive this through math. But they're called first-order systems. Simple systems like this, again, draining a bucket is another good example where there's a lot of pressure on the bucket when it starts, and you open the hole at the bottom of the bucket. But as the bucket drains, the pressure to drive the water out declines because the amount of water in the bucket declines, and overall, it'd have this same exponential shape. So really, the only thing we have to figure out is what is this time constant? And this is the function we want. And whether it's got a 1 minus or whatever, those are details that you'll get later on. It's really this exponential nature of the response of the capacitor voltage to a step on the source. That's what we care about. So we're going to do it two ways. One, we're just use some intuition, and then we're going to use some unit analysis. The first intuition step is this. If we have a really high resistance here, it's going to limit the amount of current that flows. Because, of course, we know that I, for the resistor, equals V over R. And this is V resistor here, of course, right? And I is the same through both of them because they're in series. So if we really crank up the resistance, that's going to slow down the charging of the capacitor. In the bucket analogy, that's a smaller hole in the bucket that it takes more pressure, voltage, to force out a smaller current. So if we have a high resistance, the thing is apparently going to charge more slowly. So this tau is apparently proportional to R. So now we know how R gets in here. The next question you might have is, well, how does the capacitance get in there? Well, remember to write down its relationship, that Q equals CV, and actually, I think I want to write that the other way around. I want to write that the voltage across the capacitor, Q equals CV, so C over Q over C. As the capacitance goes up, it takes more and more charge to change the voltage. So if we had a really high capacitance, and then we pour lots and lots of charge in through the current, the change in voltage would be slower because the voltage is inversely proportional to the capacitance. Conversely, if we had a very small capacitance, then it doesn't take very much charge at all to bring this capacitor voltage up to the source voltage. So we see that if we want to charge the capacitor quickly, we'd like lots of current, that'd be a small r, and we'd like a small capacitance such that when we flow the current in, a little bit of charge quickly charges the capacitor up so that Vc equals V source. In other words, this time constant is proportional to R because long time would correspond to slow charging and therefore large R to limit the current. And it seems to be proportional to C because large C will delay the voltage building up. So both large R and large C seem to relate to large time constant. So that's the intuition. If you were thinking about blowing up a balloon and then asking how long does it take to the balloon to collapse, to blow all the air back out, how tightly you squeeze the little air nozzle at the input of the balloon would be resistance. More resistance goes slower. And how stiff is the balloon? How much does it want to push that air out? That's the capacitance. So that's the reason those two terms are in there. So the last thing we want to do then is do a little unit analysis to try to get a guess how R and C might relate to this time constant. So let's just take right here. And since I already know the answer, I know what I'm supposed to do. I'm going to multiply resistance times capacitance in terms of units. So this is ohms from Ohm's law, and capacitance is in farads. But neither of those are fundamental units, so let's expand that. From here, we would see that V equals IR. So ohms is volts per amp. rearranging Ohm's law a little bit. And from here, we see that farads is charge per volt. That's coulombs, too many C's here, per volt. Coulombs is the unit of charge. C, capacitance, is the symbol for capacitance with units of farads. Well, this seems already good. Those two divide. What else can I do here? Oh, hey, I know how amps, I can do something there. So coulombs, amps is a coulomb per second. Oh, the coulombs cancel out. And it turns out, very interesting, that resistance times capacitance, an ohm times a farad, is a second. And that is our hint. Remember that we found high resistance and high capacitance both seem to slow the system down. So it turns out that is the time constant. This is called, cleverly, the RC time constant, a formula that's not hard to remember if you remember its name. And so I can now, right here, do this, RC. And I actually have the solution I wanted. This tells me, for an RC circuit, what does the voltage across the capacitor look like in response to a step on the source. And we see that it's got this character that before I step the source, we would have 0 voltage. And then when I step the source, the capacitor lags. It starts out at the same voltage, 0, and then comes up slowly with this exponential behavior to come up to the same voltage as the source. And the key element is how slowly. And how slowly turns out to be the product of the resistance and the capacitance. This is super important in almost all electrical engineering because it turns out virtually all devices have both resistance and capacitance. And you'll see this behavior, which we'll explore in the lab, by driving a step function onto our device and watching this behavior. If we stepped this back down at some point in time, the RC, the exponential would happen the same. It would have a decaying exponential. It would be that same function. We had the same shape. We just turn it upside down because we're stepping down instead of up. So this behavior, this rising and falling kind of wave-like shape, is common to almost all electrical engineering components. And again, super simple equation to remember. And really, these are the two interesting parts. It's a decaying exponential, and the time constant is RC.